A lot has happened since the last video. Mainly I created two energy harvesting PCBs and extended the software for the ZBS243 epaper text to be able to read the BME 280 temperature and humidity sensor. But as the title of the video suggests, this is more about the lessons I've learned and the project update. If you haven't seen the last video, I recommend watching it first. Let's start with the software. There are two parts, the text software and the access point software. The text software initiates communication with the access point, and if there are any changes to the current image, it requests the data and updates itself. The access point software stores information about all tags on the network and is used for managing them. It also knows what each tag should display at any given point. Until now, it has not been possible for a tag to send any data back to the AP, other than its temperature, battery voltage and the usual protocol data. For this project I needed a way to be able to send additional sensor data back to the AP. Luckily, Jelmer and Nick made it possible to have the so-called tag return data, short TRD, which provides a mechanism for sending up to 90 bytes of custom user data from the epaper display to the access point. But there was still some work left to do. First of all, there was no way for the access point to process the incoming data because it did not know how the data is structured. Secondly, the tag needed to be able to read the BME 280 sensor in order to send the temperature and humidity data. For the first problem, I came up with a simple data parser which can be configured on the AP using a JSON object. Since the tag return data contains an identifier to distinguish between different data structures, you can also define multiple parsers for them. The structure is a list of objects containing the identifier and name of the parser, and a list of fields to parse. The order of the fields matters as it determines the order in which the fields are parsed from the received byte array of data. A basic field consists of a name, a type and a length in bytes. The type can currently be an integer, unsigned integer, a float or a string. A field can also have two extra options, one to multiply the value with a given float value and another to specify the amount of decimal places the result should have. The amount of decimal places can also be used for float fields. The parser is also capable of parsing non-standard integer values with 1 to 8 bytes and 4 or 8 byte float values. By the way, if you are interested in the code, you can check it out on GitHub. The link is in the description. Next, I needed to extend the text software to be able to read the BME 280 sensor, which proved to be quite difficult. First of all, there is only one compiler available for free, which can compile the code for the tag called Small Device C Compiler, or short SDCC. While it is great to even be able to compile software for the tag, the compiler lacks a lot of features, one of them being dead code elimination. To make matters worse, the current text software already uses 60 kilobytes, which is almost 94% of the whole 64 kilobytes of available program memory. This gives us around 4 kilobytes to work with. Luckily, there were some features which could be disabled, reducing the binary to 55 kilobytes, giving us almost 9 kilobytes. I was hoping I could use the Bosch C library for reading the sensor, but that did not compile right out of the box for this architecture. After rewriting almost the whole library and removing as many unneeded functions as possible, I finally got it working. The code is now using 61 kilobytes, which is around 5 kilobytes more than the reduced binary. After flashing the tag, I could see the data being received and correctly passed by the access point. Nice. Next, I will talk about the hardware, which didn't quite work as I had hoped. My idea was to use a tiny solar panel to power the epaper display while storing any excess energy in a supercapacitor, which can then be used as a power source while it is dark. So I started to look for some small solar panels as well as some energy harvesting or boost converter ICs. I found some amorphous and polycrystalline solar panels which should perform quite well in low or indirect light conditions. Although looking at the specs, I thought the polycrystalline ones will provide more energy. I still bought some of both just to give them a try. I also wanted to get some monocrystalline or dye-sensitized solar cells, but these were either too big or too expensive. As for the energy harvester, I somehow came across the Texas Instruments TPS61023DRLR, which is a boost converter that can boost a 0.5 to 5.5 volt input to 2.2 to 5.5 volts. But it needs an input voltage of at least 1.8 volts for initial startup. Also, it uses 20 to 30 microamps quiescent current during operation, which is 10 times more than the epaper display. Next, I just got a cheap 1.5 farad 5.5 volt supercapacitor I found on Amazon. To power the epaper display, I decided on using a 2.5 volt low dropout regulator, which drops the voltage of the supercapacitor. Now, in theory, this should be all we need for a first circuit, but since the microcontroller of the epaper display does not have a built-in reset logic, it will log out if the supply voltage rises slowly. This is the case if the supercapacitor is discharged. Therefore, I use the voltage monitor to turn on the supply voltage only if the capacitor voltage is above 3.3 volts. Without thinking too much, I went ahead, designed a PCB and ordered it, just to find out that this does not work. But why? The reason is that the voltage monitor does not have enough hysteresis, meaning that it turns on the display, but the instant voltage drop results in the monitor turning the regulator off again. What I really needed at this point was a circuit that would turn on when the capacitor is charged to a specific level and only turn off if it drops below the 2.5 volts. So I reached out on the Electrical Engineering Stack Exchange asking for some help, and someone suggested a simple circuit using a voltage reference and a comparator, which could be tuned to the exact set points needed. This time I decided to simulate the circuit using LT-Spice before making a PCB. This proved to be the right decision because, as it turned out, the circuit would not behave correctly for voltages between 1 and 2 volts and actually enabled the output when it was not supposed to. This was due to the fact that the comparator only works reliably for voltages above 2.2 volts and the voltage reference for voltages above 1.6 volts. Therefore, I needed to come up with a new circuit. Another thing that was bugging me at the same time was that only 40% of the supercapacitor could be utilized, because the circuit is only able to use the voltage range of 3.3 to 5.5 volts in order to function correctly. After messaging back and forth on the Electrical Engineering Stack Exchange, the same person suggested using a boost converter instead of the regulator. So I took the inspiration and found a high-efficiency buck boost converter, the TPS 63805 from Texas Instruments. It not only features a power good signal, but also works for input voltages as low as 1.3 volts and will either boost or step down the voltage accordingly. This also makes it possible to utilize 76% of the capacitor, which is almost twice as much as before. The power good signal can then be used with the transistor and MOSFET to control the power to the display. I also wanted to simulate the circuit, but sadly could not get the simulation to work correctly. So I had to bite the bullet and just order a PCB from PCBWay again, who is also the sponsor of this video. But this time I won't show you any stock footage of their manufacturing process, but rather the PCB itself. As you can see, it is really high quality and the tiny BGA pads just turned out perfectly. If you don't believe me, head over to their site right now and order your own PCBs. Thanks again to PCBWay for sponsoring this video. After putting the PCB together and supplying it with my lab bench power supply, something did not seem right. The voltages were off and the PCB was heating up rapidly, as the thermal camera confirmed. After taking a deeper look at the schematic and circuit, I figured that some pads must have been bridged together. Since I don't have the tools to rebore the BGA part, I had to take it off, clean the pads on the PCB and solder on a new one. Applying a voltage resulted in the part overheating again, so I repeated the process of taking it off, cleaning the PCB and soldering on a new one, and this time it worked. Now, before we go any further, I wanted to measure the idle power consumption of the PCB, so I connected my power profiler kit and waited until the supercapacitor was charged and the circuit reached a steady state. As it turns out, it uses around 95 microamps in this state. Now, did I expect that result? In theory, the first boost converter should use 30 microamps and the second one 11 microamps. Also, the pull-up of the MOSFET should use another 25 microamps. This totals 66 microamps. So I assume that 29 microamps must be lost during conversion, as well as by the supercap self-discharging, which seems about right to me. I did try to replace all the pull-up resistors with 1 mega ohm ones, but this did not change the energy consumption at all, which I did not expect and cannot explain. I discharged the supercap and moved on with testing the solar panels during different lighting conditions. As you can see, the polycrystalline one does not work in low light conditions, only supplying 2 microamps. But if there is enough light, it is able to fully charge the capacitor. The amorphous solar panels don't work at all because they just don't generate enough energy. I then decided to connect the display using one of the flex PCBs. During the process I somehow damaged the boost converter because the PCB was heating up again. While replacing the boost converter, I bumped the other BGA buck boost converter, which resulted in the pads shorting again. I then tried to replace it again and finally gave up because the whole circuit did not work well from the start. So what did I learn? First of all, energy harvesting is really hard as every microampere of current counts. Secondly, those small BGA parts suck. And finally, take more time thinking about the circuit and elaborate on it before ordering a PCB. This leaves me off basically where I started, but I already have some more ideas for a new circuit. I want to replace the first boost converter with a real energy harvesting IC with MPPT tracking like the AEM30300 or AEM10941. This will not only improve the efficiency but also reduce the quiescent current from 30 microamperes to 0.6 microamperes and less. Next, I want to replace the second boost converter with a different package one, which will make soldering easier. Also, I want to use a better supercapacitor with a lower leakage current. But before the next video on this topic, I will work on some other projects first to really have some time to improve the design even further. I hope you enjoyed the video and learned something. If so, please give it a thumbs up so I know that you want to see more content like this. Bye!